Questions from homework that you guys want to talk about before we get started on the new stuff? Going once, going twice. Okay, fair enough. If you change your mind, you can always ask again later. Today, we're going to start talking about logarithmic functions. And in all fairness, warning for you guys, this tends to be the most difficult topic you do in Algebra 2. It's a topic that you haven't done based on my experience and what you guys have told me. So I would put on my big boy pants here for the next couple of lessons. It's logs, yes. In particular, if you have an ACT that you're planning on taking in the immediate future, this will certainly be a topic you see in multiple places. It's an important one, okay? All right, so let's start with some definitions here. So we say that a logarithmic function can be used to rearrange an exponential equation. So if I have the exponential equation, b to the y is equal to x, that is an equivalent equation to the logarithmic equation, log base b of x is equal to y. Now remember, since b is the base of an exponential equation, we stipulate that b must be positive and not equal to 1. That was one of the requirements we had on our exponential equation. So let's just kind of observe for a moment what this is, what this logarithm is really doing, right? So let's say we have something like 2 to the third is equal to 8, right? Everybody's okay with that being true? That's an exponential equation. So this is like my b, that's like my y, and that's like my x, right? So if I rewrite that as a logarithmic equation, I would say log base b of 8 is equal to 3. Or again, here's my b, my x, and my y. Everybody's okay with how I kind of shifted that around? So if I look if I look at this, what this is really answering is it tells me what power, oh my goodness, I shouldn't have put a B there, I meant to put a 2. Jeepers creepers. As this says, what power of 2 gives power of 2 satisfies 2 to the x is equal to 8. Right? That's really what that's telling us. What the logarithm is telling us is it's answering like, hey, what exponent makes this exponential equation true? Right? The name we're going to give to that number uses this logarithm function in it. So think back to all the problems we did in like 15.2 where we had to graph these exponentials and find the intersection because we couldn't solve for the exponential equation on its own. This right here is our algebraic tool to get around having to use a calculator to graph something and find its intersection. Hi, Megan. How are you?
Good. How are you?
Good. Thanks, dude. Okay. So let's do a little bit of practice here on using that definition of logarithms, eh? So the directions here say evaluate the following logarithmic expressions. So the first thing I'm going to do is I'm just going to say, okay, let's pretend that is equal to y. That gives me a logarithmic equation where this is like my b, my x, and that's a y. I'm going to rewrite that now as an exponential equation where I have b to the y is equal to x. Now this is something that should be easy to do, right? What power of 4 is equal to 16? 2. 4 squared is 16. Everybody's okay with that? Let's do another. So again, I'm going to say that that logarithmic equation is equal to, or logarithmic is equal to y, so I have an equation. Observe that there my b is 5, my x is root 5, and my y is y. So I can write 5 to the y is equal to the square root of 5. Well, I remember that the square root is the same as what exponent? So 1/2. So the square root of x is the same as or square root of 5 is the same thing as 5 to the 1/2. So y has to just be 1/2. Everybody's okay with that? Again, I could think about the same thing here, that like 16 is 4 squared, right? All right, let's do some that are a little bit sneakier. So again, I have log base 3 of 1 over 27 is equal to y. I'll label my b, x, and y. So I can rewrite this as 3 to the y is equal to 1 over 27. Now this one's a little bit trickier to see, right? So the first thing I notice is that on the left-hand side of my exponential equation, I have a whole number. And on the right-hand side of the equation, I have a fraction. Well, I know that if I have 1 over something, that means that I had a -1 exponent because that makes a reciprocal, right? Is everybody okay there? And now if I can I rewrite 27 as a power of 3? That's 3 to the third. And when I have an exponent of an exponent, how do I simplify that? Right, if I have x squared to the third, what do I have there? I have like 3 sets of x squareds, right? So that is x to the 6th. So what did I do with the exponents? Multiplied. So here I would get 3 to the -3. So the y should be -3. Does everybody feel okay on that one? Little sneakier. I had to dig out some properties of exponents that maybe I didn't remember, but that's okay. So what if I have log base 12 of 1 is equal to y? Again, I say 12 to the y is equal to 1. So what's y have to be here? 0. Very good. Hopefully you remember that any non-zero number to the 0 power is equal to 1. 0 to the 0 is indeterminate, was the term we used for that. Okay. So if I have log base 8 of 8 is equal to y, how do I rewrite that as an exponential equation? I write b, which is 8, to the y is equal to 8, which is the x. Oh, well, y just has to be one, right? 8 to the first is just 8. It was too easy. Is that okay with what we've done so far? Not too big of a deal. I'm trying to go through this pretty slowly and really carefully. So based on these, I want to make some observations here. So from letter D, if I take any log of 1, that has to equal 0, right? Is everybody okay with that? So what we saw here. Is everybody okay? if the log base matches the x, that has to equal 1. That's what we saw here. Here we have that log base b of b to the y is just equal to y. That's what we saw here. Right? If I replace the 16 with 4 squared, that's what we have. Just simplify down to the 2. And then I don't think we had a specific example of this. Next one. If I have b to the log b of x, that is just equal to x. These last two properties or observations are going to be super, super important going forward, because what we're seeing from these observations is that we can use log base b to cancel exponent base b, and then we can use exponent base b to cancel log base b. This is going to be the foundation for how we solve exponential and logarithmic equations, and really how in the future we'll go ahead and simplify logarithmic expressions. This idea that log base b cancels exponent base b, and that in return exponent base b cancels log base b, is maybe the single most important concept that we're going to see in this section. If you take nothing else away other than that, you'll not be too bad off. That piece becomes critically, critically important. Okay. Time for a little bit of vocab. So the first term is called the common logarithm, and that is log base 10. So log base 10 is what we call the common logarithm. And we abbreviate the common log as just log. If you look on your calculator, you'll notice that there's a log button here on the left-hand side. If I press that, notice there's no subscript here. That means this is the common logarithm. It means it's log base 10. So if I did log base 10 of 10, what would I expect to get? One, right? That was observation 2 from over here. And that is indeed what I get. Everybody's okay? The other piece of vocab we have is called the natural logarithm. And that's log base e the natural log is abbreviated as ln. Again, if you fired up your calculator, you'll notice that below the log button is the ln button. That means log base e. So if I did the natural log of e, I would expect to get 1. Does everybody feel okay so far? Okay. Let's do some more examples here. All right. So it asks us here to solve. So a is equal to log of 1,000. First thing I'm going to do is identify the base of the logarithm since it's not written here. When we just write log with no base, what do we understand the base to be? 10. So to simplify this, what I'm going to do is one way is I can think about rewriting 1,000 as a power of 10. What is 1,000 as a power of 10? 10 to the third, right? Because there's 3 zeros. So the log base 10 and the exponent base 10 can cancel, leaving me with a 3. Or I could write this as the exponential equation 10 to the a is equal to 1,000. And 1,000 is 10 to the third, so a would be 3. Either way of thinking about it is fine. In general, from here on, I'm probably going to try to think about things this way, because I'd want to reinforce that idea that exponent bases and log bases cancel each other out. That's an idea that I really want to hammer, so I'm going to start doing these simplifying problems this way as opposed to rewriting them as exponential equations, but it's not wrong to do it as an exponential equation. Okay. Here I have b is equal to log of 5th root of 10. Just like before, I observed that the base on the logarithm is 10. I can rewrite the 5th root of 10 as 10 to what power? The 1 over 5, right? If I have the nth root, that's the same as the 1 over n power. Those guys can cancel, so I'm left with just 1/5. Once again, I observe that this is log base 10. 0.001 is 1 out of 100, right? I know that's the same thing as 100 to the negative 1. 100 is 10 squared. Exponent of an exponent, we multiply. Oops. And then those guys reduce, giving me a negative 2. Too quick? Are we okay? Stop me if it's going too fast or if you're confused. So the next one is we have e to the natural log of 5. The first thing I would do is I would think about, okay, what's the base of the logarithm for ln? That's the natural log, right? That was was logarithm base e, right? Exponent base e and log base e will cancel. So that's just 5. So here we have 2 is equal to log of x. What's the base of this logarithm? I don't see anything written there. 10. So what exponent base do I need to use to cancel that logarithm? 10, right? So I'm going to write the left-hand side as 10 to the second. And I'm going to write the right-hand side as 10 to the log base 10 of x. Again, since I'm doing that to both sides of the equation, it's okay. The reason why I wanted to do that is the log base 10 cancels with the exponent base 10. So we just have that 10 squared is equal to x, or x is equal to 100. Either is okay. Is that okay with everybody? Sure. Okay. The next one, we have the natural log of y is equal to 5. So what is the base on the logarithm, natural log? It's e So what exponent base do I need to cancel the log of e, or log base e? Needs to be exponent base e. The bases for the two have to be the same. So I'm going to have e to the left-hand side of my equation equals e to the right-hand side of my equation. Exponent base e cancels log base e. So we have y is equal to e to the 5th. Everybody's okay with that? Okay, did some stuff with that. So again, if I just want to do like log of 15 on my calculator, I can just do log 15. If I want to do natural log of 15 in my calculator, I just do ln 15. right? We just type it in and press enter. Like 10 of your problems from the homework set are literally just doing something like that. Woof, that's hard. No, not really. You think it is? Okay. Well, I hate to see when you get to the stuff that is actually hard. Okay. So at this point, we've kind of talked about like what a logarithm is, how we evaluate logarithms, right? If I did ask you to do log base 2 of 16, you now know how to do something like that, right? What we want to do now is explore some further properties of logarithms. These ones will be also something you'll use a lot. So these are good ones to make sure that we remember. So there's 4 of them. The first is the product. I'm going to call it property. So this says log base b of xy is equal to log base b of x plus log base b of y. So what's happening here is that multiplication inside of the logarithm is changing it into addition of 2 logarithms, right? The next one is the quotient property that says log base b of x over y is equal to log base b of x minus log base b of y. So notice here, division inside the logarithm is turning into the difference of 2 logarithms. The numerator is the positive logarithm and the denominator is the negative one. That order matters. And then there's the power property that says log base b of x to the c is going to equal c times log base b of x. So a power inside the logarithm turns into a coefficient outside the logarithm. Due to the level of this class, I'm going to skip proving these. Oh, there's one more. I'm sorry. The one more is called the change of base formula. And this says that log base b of x is equal to log base c of x divided by log base c of b. So the change of base formula, when I was a high school student, was super important. Because if I wanted to do something like log base 2 of 6, what we had when I was in high school was like a scientific calculator, where we had the log and the natural log button on our calculator, but we couldn't do the log of any base. So if I want to do something with like log base 2 of 6, I would do that as log of 6 divided by log of 2, where I've used the change of base formula and picked the new base of my logarithm to be 10. Or I could have done it as the natural log of 6 divided by the natural log of 2, where I picked the new base of my logarithms, the c, to be e. But you guys don't really have to worry about this. The reason is your calculator can do logs of different bases. To do that on your calculator, you press the math button and then scroll down to Command A, which says log base, which allows you to type in a base of any number you want, as long as it's greater than 0 and not equal to 1. And it allows you to type it in exactly as it looks like on your sheet of paper. Everybody's okay with that? Now, unless you have like the old, like TI-83, like green and black screen, like really rectangular looking calculator, I don't think you have to use the change base formula. You can just use the log base command. But I've seen a couple of us still have the old school calculator, so you would have to worry about the change of base formula if you have one of those older graphing calculators. I think even when I was in high school, when we first did this, we weren't even allowed to use our scientific calculator. You had to look up these values off of a table to use the change of base formula, where you had to like look up log of 6 and then look up log of 2 and like write down the numbers and then do the. It was a really big pain. The calculators really made life a lot easier to do this stuff. Okay. With these properties of logarithms, there's two types of problems that we're going to be asking you to do. We're going to talk about what those two types of problems are, do some examples, and we're out for the day. Sound good? So the two types of problems are expanding, and then the other is compressing or condensing. I've seen those two terms used interchangeably. When doing expanding, the order in which we want to apply the properties are going to be quotient, product, and then power. That order is critically important. You're doing it in the correct order. The only exception would be is if somehow the order of operations say to do the exponent before you wanted to do multiplication or something, right? Like if I had a times b to the second, the order of operations is telling you to do the power before the product, right? Otherwise, if it was just like this, you do the power first, or the product first and then the power. All right, let's do a couple of examples here. So let's say we have log base 3 of 5x, and we want to expand this. That's the direction. Actually, let's... I guess we'll write it this way. So when we say expand, what we're saying is that you want to start with a single logarithm and break it down into as many logarithms as possible using these properties of logs. Oops, I had 4x there before. I don't know why I wrote that 5x. Okay. So according to the directions I just gave you, the first thing I'd want to look for is a quotient property. So I look inside my logarithm. Do you see any division going on inside the logarithm? No. No quotient property to do there. Okay. Then we'll go to the product property. So then I'll look at the stuff inside of my logarithm. Is there any multiplication going on inside my logarithm? You should say yes. What is being multiplied? 4 and x, right? There's like a multiplication symbol in between the 4 and the x that we know is there, but we don't bother to write. So if I apply the product property then, I will write that as log base 3 of 4 plus log base 3 of x. So far, so good. Now, I'm going to take a look at each of these logarithms and say, okay, I'll look on the inside and see if there's any power properties. Do we see any power properties going on? Well, look carefully, because there is one, but I've hidden it because I'm a sneaky jerk. Do you think it's happening with the 4 or happening with the x? It's with the 4. So how can I rewrite 4 so that it has an exponent? 2 squared. Yeah, that'll do. So there I can use the power property on 2 squared. So the exponent inside the logarithm becomes a coefficient outside the logarithm, and then everything else just kind of stays the same. So this would be my final answer. Let's look at another example. Let's say we have 3ab to the 5th. I'm sorry, log of 3ab to the 5th. Do we see any division going on inside the logarithm? No. So no quotient property. Do we see any multiplication going on inside the logarithm? Yes. How many multiplication symbols are there inside the logarithm? 2, right? There's one between the 3 and the a, and another between the a and the b. So how many product properties are going to be going on? 2. So to apply the product property, I'm going to have log of 3 plus log of a plus log of b to the 5th. Everybody okay with that? So every place there's a multiplication symbol, we just have a break, an addition symbol, and a new logarithm around whatever the other piece was. So far, so good? Now let's look for power properties. So log of 3, is there a power property going on there? Last time, Mr. Kulik, you rewrote 4 in a weird way to get a power property. Can we do that with a 3? No. Why not? Because it's a prime number. Exactly right. Excellent. How about log of a? Any power property going on there? No, because it's just to the first. Okay. How about log of b to the 5th? Yes. So the first 2 logarithms, I'm just going to recopy exactly like they were. But that last logarithm, the power 5, is going to become the coefficient on the logarithm. And then everything else just kind of stayed the same. Ooh. So far, so good. All right, one more. Oh, so our final answer then is just this stuff. All right. One more example. Okay. Here we have the natural log of 2x over the cube root of x cubed minus 5. I'm sorry, the square root of x cubed minus 5. What's the first thing we look for? Quotient. Do you see any division going on inside the logarithm? You betcha. So the quotient property is going to be the natural log of the numerator minus natural log of the denominator. So far, so good. Next thing we'll do is look for product properties. So if I look at natural log of 2x, is there any multiplication going on there? Yeah, right? There's a multiplication going on between the 2 and the x. So I'll rewrite that as natural log 2 plus natural log x. Now let's look at the natural log of the square root of x cubed minus 5. Is there any multiplication going on there? No, right? It's just the stuff under the square root, so that's all going to just stay where it is. Now let's look for power properties. If I do the natural log of 2, is there a power property there? No. Natural log of x, is there a power property there? No. Natural log of the square root of x cubed minus 5, is there a power property there? Okay, yes. What is the power? It's not 3. It's not 1 over 3. I can think about that square root as a 1/2 power round everything. So the power property going on here is 1/2. So far, so good. Anything more I can do? Who's suspicious about this x cubed here? Feels like there should be a power property to do there, right? It turns out there's not, because remember the power property looks like this. Here we have the powers attached only to the 3, not to the entire thing in there. And because it's not being multiplied, we can't break it apart, because logarithms are not distributive. So I can't take log of a plus b and write it as log of a plus log of b. If you're ever in doubt as to whether you can do something like that, you can just do a little test. You can say, okay, what if I do log of 2 plus 3? That gives me one answer. And what if I do log of 2 plus log of 3? See if that gives me the same answer. It doesn't. So I definitely know that I can't do something like that, right? So this one, it turns out that's as good as we can do. So even though there's an exponent still left in there, there wasn't another power property because the exponent wasn't surrounding the entire quantity there. It was just on one term of a polynomial. Is that okay? That can be a little tricky. The other type of problem was condensing. Here we're going to just do the opposite order. We'll do power, product, then quotient, because the idea is the opposite. We're going to take a bunch of logarithms and try to combine them down into as few logarithms as possible. So it's just the opposite steps. So let's take a couple of examples here. Okay. So the first thing we look for are power properties. Because we're going the reverse direction though, instead of looking for an exponent inside the logarithm, we're going to be looking for a coefficient outside the logarithm because we're trying to do the reverse process. So we should see 1, 2 power properties. So that first logarithm just stays the same. The second logarithm, that coefficient of 3 becomes an exponent of 3. And on the third logarithm, that coefficient of 2 becomes an exponent of 2. The next thing we're going to do is look for product properties. So instead of looking for multiplication inside the logarithm, we're going to look at the addition of 2 logarithms. So I see power property or product property happening right there. In addition, though, between that of just the addition sign, or also, besides looking for the addition between them, I also need to check to make sure the bases of the logarithms are the same. They are. They're both base 4. So I can combine those using a product property. So I'll just have x times x cubed, or I'm sorry, y cubed inside. And my last piece then is looking at quotient properties. For the quotient property, we need to have a minus sign, and the bases of the logarithms have to be the same. We notice here, they're not, right? Well, that means that I can't actually apply the quotient property there, so that's as good as I can do. Sound good? Okay, I have one more example, and we'll call it good for today. Yay? Yay! All right. So let's say we have 4 natural log A minus 3 natural log AB plus 2 natural log B. First thing I'm going to do is look for power properties. How many power properties do you see? 3, because I have 1, 2, 3 coefficients. So when I apply the power property, that becomes natural log A to the 4th. Now we have to be a little bit careful here on the second one. That's going to become the natural log of the quantity AB to the 3rd. And then the last one becomes natural log of B squared. Now remember, when I have an exponent of a quantity or of a product like that, so quantity AB to the 3rd, how does that simplify down to? A to the 3rd, B to the 3rd, right? Okay. Next thing I'm going to do is look for the product property. Are there any product properties happening here? Yes, right, I see the addition symbol. What 2 logarithms should I be combining with the product property? Because I have 3 logarithms written here. Matt? Yeah, sure. It's a little bit tricky here because it should be this one and this one. When we apply the product property, the 2 logarithms that we're combining together have to both be positive logarithms. Notice the other log has a negative sign in front of it, so I can't use that one for a product property. And then my last step is for quotients. I do have a quotient property since I have the subtraction between them. So which one should be the numerator? The positive one. So a to the fourth b squared. And the negative part should be the denominator, a cubed b to the third. Do you notice anything about the insides of that logarithm? Can reduce, can't it? So I should do that. So that's just going to reduce down to the natural log of a over b. Woo! What do you guys think? We did a lot today. That was a lot of stuff. So you guys do have, what is it? It's 37 or something? Yeah. To 98 is the new addition to your problem set. I know you've already started complaining about how many numbers that is, but like, look at some of these problems. Look at 37 through 60. These are just examples of things that we've already done, right? Like this shouldn't be too bad. Those should be like relatively pretty darn quick problems. Look at 61 through 68. Use a calculator. You're just typing that stuff in your calculator and pressing enter.
That's like 8 questions, Mr. Goulet.
Don't do 69 and 70. We didn't do the proofs there. I don't think you need to do those. Look at 93 through 98. Using your calculator. And the last problems are just these expand and condense problems that we've just got done practicing that were not tremendously time consuming. They're like one-liners, right? Yes, it's going to take you a second to get started. But after like the first 2 or 3 of these, they should be down to like, 30-second or less problems. You know what I mean? Like, it's a lot of numbers, but like none of these should take you more than a minute once you've gotten the hang of it. I would say less than 30 seconds once you've gotten the hang of it. None of them are tremendously complicated. It'll be okay. The hard problems start coming in the next section.
I wanted to show you.